Okay, so welcome to the Heidelberg Joint Astronomical Colloquium for today. It's a great pleasure and an honor that today, this week actually, we have as a guest Leonardo Testi. He's essentially from ESO and from Testi. He did his PhD in 1997 in Firenze. And then actually he did also a postdoc in California Institute of Technology between 1997 and 1999. And then he moved back to Italy and took a position at ACT. And in 2007 he moved to ESO to become an ALMA program scientist, where he is currently still working. And he's interested in many things, scientifically. We have been also collaborating on planetary disks, and of course he's the man to talk to when it comes to your ALMA observational plans. He will still be here until tomorrow afternoon, so if you want to talk to him, then you can contact me or just come to the Albert Uberstraße 2. And well, so I won't wait too much more of your time. So let's welcome Leonardo here to Heidelberg and let's hear the talk.
It's very nice to be here, and I hope I will entertain you on what ALMA is, what ALMA can do, what ALMA is doing. Actually, I will focus a little bit of the talk on ALMA results from the people, from this group of people that are working on star formation, planet formation at ESO. And then I will also briefly update you on the prospects for the ALMA capabilities and what ALMA can do for you in the medium to long term. Okay, so I thought it might be nice to reflect a little bit on ALMA as it started, what was the goals and where we are now. So is this early days of ALMA? Matt McCogan is always great in finding these things. So this is from a book in 1889, The Conquest of the Moon, where they had this nice picture with 25 of these large single-dish telescopes. They were not telescopes in this book. And so Mark always says, well, you know, you just picked something that was written many years ago. And that's not exactly true, obviously. ALMA was not thought in the 1889, but actually the origins of ALMA are 100 years later than that. So in the 80s and the 90s, when the first results from millimeter interferometers were coming, and people realized that, you know, around the young stars you had compact emission in the submillimeter that might be interesting because maybe you could form planets there, and so it would be nice to resolve them and see how the disks look like, how the planet formation goes, or some crazy people like me try to do large maps of molecular clouds to see the structure and see these compact blobs here and there, thinking maybe this relates to the fragmentation of the molecular clouds. And these were initial results, very limited in scope, and this was the seed of the idea that we needed something larger, the same jump that centimeter radio astronomy did, going from the initial interferometers and the VLA. So that was essentially the background of how ALMA came along, and it came along in the three regions, in what are now the three ALMA regions at that time, with ideas in Japan, the ALMA, in North America with the ALMA, and in Europe itself with the LSA. And soon people realized that it was better to build a single instrument rather than a single facility, rather than continuing in this three independent path towards smaller facilities, because a larger putting together the resources from the three regions would have allowed to build really a transformational facility, something that was a huge jump from what was available and what would become available. So essentially, ALMA was designed from the beginning to basically be a jump of at least 2 orders of magnitudes in sensitivity and angular resolution with respect to what was available at that wavelength. And if you think of it in these terms, it was really a great vision, a great dream at that time. You know? Okay. And so the rest is history to some extent, and AO and ISO got together in 1997 to build this giant thing. Japan joined in 2003, and later on other little partners accreted onto that. And the vision that we eventually had was to build an array of telescopes with at least 50 12-meter antennas for interferometry of 12-meter diameter, working with a frequency range between 30 gigahertz and 1 terahertz, which in wavelength means from 10 millimeter to 0.3 millimeter, sampling exploring the essentially most of the cold universe, with baseline separations between the antennas going up to 16 kilometers, which correspond at the highest frequency to an angular resolution better than 10 milliseconds. And all this complemented by a smaller set of antennas dedicated to recovering what we call in our jargon the zero spacing. So essentially, obviously overcoming the problem that you have when you observe with an array of telescopes doing interferometry, that you cannot put 2 antennas closer than the diameter together, because otherwise they collide, and so there are some special frequencies that we are not able to measure in the sky, and the compact array has been designed and constructed to provide this inner spacing. The 3 science goals, the 3 dreams that we had, our guiding principles when we were building ALMA, were essentially, in simple words, were to build a telescope that was sensitive, had high angular resolution, high image fidelity, and covered the sub-millimeter regime. And the science goals were to detect and map molecular and atomic gas in galaxies, even normal galaxies, non-dense normal galaxies, which was essentially almost impossible at the time of the design. Map the gas and dust in protoplanetary disks to probe planet formation, and in general provide high fidelity imaging at sub-millimeter wavelengths at an angular resolution that was comparable or better than the one provided by the 8 to 10 meter telescopes in the optical with adaptive optics. Okay? So to complement that part. And actually, this last, if you think of it, is the most difficult of these goals, because the others, in some sense, you can arrive with a brute force approach. If you need sensitivity, you just build more antennas. If you need more angular resolution, you just build longer wavelengths. But providing high fidelity imaging at high angular resolution with an interferometer is inherently a difficult problem, because interferometers are not high fidelity instruments by design, okay? Because they sample the UV space. So that has been the most difficult one, and actually the drive for the number of antennas. The more antennas you have, the better you sample the Fourier transform plane of the sky, and the better image you get, the more fidelity image you get in the end. Okay, this was the dream, to have an instrument that does everything, the ultimate instrument at sub-millimeter wavelength. Obviously, as everybody at some point, we had reality in the mid-2000s, when we discovered that actually the budget was not large enough to build everything that we wanted. And so at that time, we decided to make some choices that define ALMA as it is now. Okay? And basically, we decided to defer some of the capabilities, some of the frequency bands, and some of the capabilities that basically defer them into the development plan. And I will come to this at the end of the talk, and I will tell you what are our plans for the future. So I think we were very successful in setting up this way, in such a way that we did something that was not, that was constrained by the budget, but was delivering key and new science from the beginning, but then also the possibility of being upgraded to deliver even more science in the future. And there are many tales and things that I could tell you of the construction process in itself. It is always entertaining to discuss from the discovery of our rodent, that is the typical little animal that is blocking you from building any telescope, and to the more difficult problems of actually understanding the atmosphere of your telescope when you want to phase up 4 millimeter DLBI, which is the more dry and technical thing. So I'll go for the rodent because that's nicer for most people rather than having a difficult conversation about space stability. And basically this is from one of our early environmental studies where we had to find out that we were not disturbing this nice animal, which is something this big, and is in between the mouse and the rabbit, and lives at 4,800 meters near the ALMA site. The ALMA site that you see there is an altiplano in southern Chile, and in the Andes, close to the border with Bolivia and Argentina. And this place here, which is the center of the array, is at 5,050 meters, roughly speaking, altitude. And it slowly goes down at the edge of this perimeter to 4,800 meters. Okay? So it's a very large altiplano. The sides there is basically from one side to the next is 20 kilometers. Okay? So it's a huge altiplano at almost an average of 5,000 meter altitude. And the reason, obviously, to go at that altitude is that the main enemy of submillimeter observations is the water content in the atmosphere, water and oxygen content in the atmosphere. In fact, also the oxygen too is a problematic line. And so you have to go in a place where living is difficult for us. And so observing is easier in the submillimeter. So that's what we did for ALMA. But when you go to these remote places where it's difficult to live, you also find some inhabitants that don't live anywhere else. So you need to make sure that you are not destroying their habitat. That's what I needed always the telescopes find something like this. And this was in particular the list. So this thing here are the places that we had to avoid because they were the living and breeding spaces of these little animals. So we had to avoid them with our roads and things as if the colonies of these animals were fixed in time forever. So that's sort of the game that you have to play when you build a telescope, when you do an environmental. I'll leave you to imagine how we did the counting of these beasts. It's not easy. Every one of you who had a little rodent as a kid in their home know that they live at night and not during the day. So how to find them, if you want to know, we can discuss later. But anyway, we managed to do this and to build the infrastructure. And finally, in 2011, we could start doing observations with early science. So we decided from the beginning to start science in steps. So we started with a partial array of just 16 antennas and 4 frequency bands and limited correlated modes, which already at that time was the absolute best submillimeter array on Earth, even in this at early times. Okay, and to give you a scale, and this picture don't give you the scale of this observatory, to have it more on something that perhaps you can connect to. This is the compact array. So when we are in the compact configuration, we essentially fit in the area of the castle and the market at that time. And this is the main array, so 15 15 12-meter antennas, and the compact array sits essentially on the cable car station there. Then obviously, since it's an array, we can reconfigure the antennas to get more angular resolution, as I said, up to 16 kilometers. And I tried to fit them on Heidelberg, but Heidelberg is not a large city. And so basically I could not fit it between Heidelberg and Max Planck there. And I had to expand the view. And basically from the Max Planck, if you put on the Max Planck side our farthest antenna to the south, then the farthest antenna to the east is here, which I think is the industrial thing that we were looking from the upper floor the other day. So this gives you the scale of ALMA when it's totally expanded. Essentially, this is the center of the array, this is the south arm, this is the east-west arm, and this is the northern arm, just to give you a scale of also of the size of this altiplano at 5,000 meter altitude. It's really impressive as a site. Okay, so so far we have done 3 cycles of science observations, and we are just started the 4th cycle of science observations. Typically, we are still in what we call early science shared risk. So the array is growing, the capabilities are growing over time, and if you look at it this way, in the first 3 cycles, we had about 30 to 70% of the total collective area of the array, so the raw sensitivity of the array, and the maximum separation between the antennas up to a few kilometers, which is a small fraction of the total 16 kilometers. And already at the time is the most powerful millimeter observer, which implies essentially that a lot of people want to use it. So if you are one of the community that is trying to get ALMA time, you have to go through the shrinking thing of the subset of yourself, who is selecting which are the best projects that should get time at any time. Just to give you the numbers that we have reached now on cycle 3, we are now at almost 1,600 proposals, which is the largest number of proposals ever received by a ground-based observatory for a single cycle. And over 400 of these have been allocated time in high priority and have been executed as we speak, essentially. The completion rate that we expect typically for these 400 projects is of the order of 80%. Hopefully we will do more. But if you are in those 400, you have a good chance of getting your data, even if we are still in early science and shared risk. The maximum baselines that we are offering and that we, this was 13 October 15, so. Has been 10 kilometers, and we just executed the long baseline campaign, and we are back into the more compact configuration now. Okay, and I will go later on the future of ALMA, what will be available later on. I will be more specific on the capabilities. I thought it was not really important to go on the specifics of the past things, but rather on what will be available for the future. I just wanted to flash some of the results that we have been obtaining. Just to give you a scale, I'll give you a few examples from the early universe, for example. These are 2 observations, one from a regular cycle, this one, of a normal galaxy at redshift, I have to admit that I forgot, but around 3.5, if I remember correctly, in which essentially there was a detection of a narrow carbon plus clump close to a Lyman alpha cloud, so essentially the inflow of gas into this primeval galaxy at high redshift. And this example here instead is a gravitational lens from the science verification data from the 16-kilometer baselines last year. This is the HST image in which you essentially see the lens, so it's an elliptical galaxy in the not too far universe. And then if you are here, not there, you can see that there are 2 little arcs here, which is the lens that is barely detected in the infrared. And this is what you observe with ALMA triangular resolution. So you see the Einstein ring essentially of the lensed galaxy, and on the other side you have the image reconstruction with a advanced model of the clumps at again redshift 3 and something of size of the order of 100 parts, which are the units that are doing the star formation in this distant galaxy. And basically here was the helium and the molecular line, and then the stellar medium that underpins the galaxies. Another results from an extragalactic astronomy has been mostly on the feeding the supermassive black holes and establishing the local universe. Here you see essentially an overlay of an HST image and the ALMA observations of the molecular ring that is fueling. There are some streams that you don't see very well here, but they are fueling the inner accretion disk of the black hole. And this one is associations of NGC 253, where basically you see the dense gas that is participating in star formation with ALMA, and also in that particular case it was detected a molecular wind that is providing the feedback from the huge star formation event in the center to the rest of the galaxy. In the area of planet formation, obviously there has been a lot of results on protoplanetary disks, from the structure of the dust emission, which we will see a little bit better in a minute, to chemistry of the gas within the disk. And for the first time, it was detected a complex organic molecule in protoplanetary disk, which is still a relatively small molecule, CH3CN, that is the first of this type ever detected in a protoplanetary disk. So if we look back to the outcome of early science from ALMA, from cycle 0, for example, and I look at cycle 0 because it has been closed, all the data has been delivered since a couple of years, so you can take a step back and look at how it went. These were basically the distribution of the categories of science that we were doing as projects, so that we were scheduling at the telescope. Essentially, 1/3 dedicated to extragalactic astronomy, active galaxies, and galaxy evolution. A little bit, almost 50% dedicated to the interstellar medium star formation and disk and planet formation, and the rest dedicated to stars, cosmology of the solar system. And on the other side, you have what came out as science delivered in terms of paper published, which is still very similarly balanced. There is an overproduction of our galaxy evolution colleagues, which are able to produce a number of papers per photon, which is surprising at times. Good for them and for us to some extent. And the other impressive graph, I think, is this one. So this is the fraction of ALMA projects that produce the publication from cycle 0 as a function, well, actually all cycles, so in this case. The fraction of ALMA projects that produce the publication as a function of the time since the data was delivered to the users. So it's a convoluted way, but what it means is that data that were delivered to the users, say, 2.5 years ago, 30 months ago, have produced a publication in 80% of the cases. So this is an extremely high fraction if you compare to these normal outcomes out of telescopes. And the interesting thing is that it seems rather flat at this level. So we basically produce science at 80% fraction. Okay? This is partly due, in my view, to the fact that ALMA, as I said at the beginning, was designed to be something completely new with respect to the past. So wherever you look, you find something that produces an interesting result. Okay? So that was the reason.
What are the papers where the curve is going down? Are these rejected papers?
No. This is simply telling you that if you receive of the projects that were delivered data 10 months ago, only 20% have produced the publication.
Yeah, but there are, the curve is going down in some. It has also local minima.
Oh, you mean
Yes.
this
Yes,
weekly?
yes.
Oh no. I think this is binned, okay? So it just means that this bin here has a lower publication fraction than this bin here and this bin there.
It's not cumulative.
It's not cumulative, exactly.
Ah.
It's not cumulative, that's the point. Yeah, that's right, thank you. Okay, I want to spend some time on actually doing some publicity to what we do at ESO by the group of people that is working on these topics, star and planet formation. They are mostly young fellows or students, and let's remove their faces for a minute. And they work mostly on planet formation. Okay, so planetary disk structure and what you can derive there in terms of understanding the first phase of planet formation. The structure of molecular clouds, studying, for example, filaments in the galactic plane, or the feedback from high mass star formation. This complicated figure is actually showing you the red and blue shifted high velocity gas coming from high mass star forming region in a complex, in a large complex of our own Milky Way. And basically, they do this by combining a lot of data from different telescopes, but I'll focus on a few examples based on ALMA data to show you the nice things that we get. One of the things that they like to focus very much is basically connecting the larger scale of the molecular gas and dust in our own galaxy, in this particular case, in the inner regions of our own galaxy. So the center of our own galaxy is here, so Sagittarius A star, and then this orange thing are millimeter continuum emissions. So this is dense gas, and this is Sagittarius B2, one of the star-bursting region, highest star-bursting region in our own galaxy. And one of the things that some of us focus on, for example, Alan Gisborne, is trying to figure out the physical conditions from an observational point of view of the gas in this region, and how and if this gas can form a star in such an environment, and then they feed these numbers to something like Diderik, who then can run these beautiful models and tell us where we are wrong and where we are right, hopefully. Steve Longmore actually started looking at these particular objects a few years ago, showing that it's a very particular cloud with very high density and very high mass, and yet not forming a star effectively. So that was a perfect target to look at it with ALMA at high angular resolution to understand its internal structure, whether it was what was the support that was keeping this cloud together with very little star formation. So in fact we had this project. Unfortunately it's not very nice, the contrast here, but basically ALMA resolved the structure of the cloud. You can see the contours, but resolved the structure of the cloud in many different small cores and fluctuations that then can be studied in detail, and Christoph Federer is now trying to make sense of this in the context of how the internal structure of the cloud is connected to possible star formation, and what is actually sustaining it from collapsing. And there is an interesting debate between him and Diderik and the study that at some point will converge, I presume, or maybe not. But in any case, it's interesting to watch from a distance, from my point of view at least. I provide the data and fight for the interpretation. Another important aspect, this highlights a pre-star forming core, if you want, in a particular environment. Another area in which we invest time is understanding the effect of star formation on the parental cloud, as I showed in the initial slide. And this is another example from Adam Eastwood of a very well-known object near home that every time you look at it, it shows you something more interesting. So this is the Orion. Of course, you have recognized the trapezium here. This is the Orion Nebula cluster. But this is the interesting point here, where there is a massive star that is driving this explosion, which is observed in the infrared as these fingers. And well, Adam and John Baldwin decided to look at it with ALMA in molecular gas to see the effect of this explosion onto the cloud itself. And this is what you see. Without the effect of extinction, cloud in your eyes, you see the full breadth of the extinction. So blue fingers are moving away from you, red, well, vice versa. Blue fingers are coming at you, obviously. Red fingers are going ahead of you, and the green is on the plane of the sky. So essentially, these explosion fingers here were actually all on the sky. You see that they are mostly green, but there is a lot of explosion. It's almost spherical and not distributed as in the infrared.
Right. The spikes are given by real, or is just something that's wrong?
It's real. No, that's all real. So this is an image which includes the compact array and the main array. So it's really a full reconstruction. Okay? So the only thing that is not full is the full zero spacing, so the zero velocity, the cloud velocity, because there the filtering effect is very large. So the green is actually produced by excluding some velocity channels.
What wavelength is that?
That's the 0, 2 to 1, so it's at 230 gigahertz, 1.3 gigahertz.
No, understood. What's this?
Well, there is always the usual discussion between Jonathan Tan and John Barr. and all the rest. Actually, Jonathan Tan against the rest of the world. So the most commonly accepted idea is that basically these are the three culprits. Okay, so that they basically had a three-body interaction, something like 700 years ago, something like this, and created the explosion. While Jonathan Tan has a different idea. One of these is actually coming from a different direction and perturbs the existing system. But in any case, 700 years ago, there was, or 500, I don't remember the exact figure, there was an interaction here, a multiple body interaction here between protostars, and this created this release of material. The interesting question is how frequent or how rare this is in general. And I think we don't know it yet, in the sense that so far we had the sensitivity and resolution to see this type of things only in Orion. Maybe with ALMA we are able to see this type of explosions also in more distant regions, and so we will be able to figure out that this is a common thing, so it's just very special. The other thing that I wanted to obviously spend a little bit more time, not too much, otherwise we will go to sleep, is protoplanetary disks. This is my most unfair comparison, the H. Centauri observation of the protoplanetary disk with the overall array many years ago, and the ALMA observation. Of course, in the video there was a lot of things. So this was the best observation before ALMA of this protoplanetary disk, which resolved the disk radially, but this looked relatively smooth. Then you all know what I'm going to show. This is the ALMA view with the long wavelengths of this same disk. Essentially, the size of this is this size. So essentially, this shows the power of ALMA in resolving the structure in protoplanetary disk, which was one of our main goals for the construction of ALMA, and showing essentially what we believe may be the tracks of forming planets in the disk. Interestingly, as soon as we saw this, now obviously we see three main dark patches here. One here, one here in the distribution of the large units, and one here. And if you consider this one here, the most external one, is actually in a region where the original observation, so this observation here, showed that the disk, if you plot the Q parameter as a function of radius, it goes into possibly an unstable region exactly at the location of this hole here. Okay? And so what we thought obviously is that maybe there are planets formed by the gravitational instabilities there, and if there are, then they should be relatively massive, so they should be detected. Mind you, that is not that trivial, because if you look at the intensity profiles here, these that looks like dark, very dark rings are dips in the emission, but they are not very deep. It does not go exactly to zero. Okay, it's a moderate depression on the emission. But nonetheless, we tried to find the planets, and actually we could not down to a level which is not very high, in the sense that we could exclude companions here with masses of the order of 10 to 15 Jupiter masses, which is relatively large, even for gravitational instabilities. But in the meantime, there were several papers that actually described this structure as potentially caused by planetesimals that are still in essentially the large grains within the disk. So it might be that these dips are actually not caused by large planets, but rather embryos of planetary systems. And this brings to the next topic, how you get there, and how you measure the growth of these solids in disk, which is one of the things that obviously his group has been devoting a lot of time during the years. I want to skip a little bit because I want to go directly to the result, but let's go first to this one. One way that we use observationally to probe the size of the grains, which is a classical way of doing it, is to say very simply that if you have a grain distribution in your disk, and when you observe them at a wavelength that is comparable with the grain size, then the opacity becomes great, essentially. And so there is a change in the slope of the emission. So if you reverse this process, this reason, and you say, okay, I am observing between 1 and 3 millimeters, for example, and I observe the spectral slope of the emission of the dust grains. If the grains are much smaller than my wavelength, then I have a slope which is relatively high. Okay? If my grains are of the order of my wavelength or larger, then the slope has to be low. And so basically this was a result that was known from a few years before ALMA, that many of the protoplanetary disks in star-forming regions show clear evidence for large grains. And to guide you in this axis is proportional to the disk mass, to one type approximation, and this axis, as I explained, is proportional to the grain size. So essentially, most of these disks show evidence for grain growth to a certain level. This is all nice until you try to explain it with a model, as Dean was doing with kids, because basically it is difficult to explain this population of low mass disks with large grains, because the balance of the transport of grains, the fragmentation, and the growth does not work in your favor in the models. Okay? So one of the strong predictions of the models is that you should have a gradient of dust properties, and these gradients also depends on the characteristics of fragmentation and the transport of the grains inside the disk. So one thing that we tried to do with ALMA was to try to verify these model predictions by trying to measure the size distribution as a function of radius in these disks. This is not an easy process, and I do not want to go to the gory details on how we do this, I'll just go into some of the results that you show here. And this is the proxy of the spectral index that we measure as a function of radius for a number of these disks, combining data from the DLA, ALMA, and other emitter interferometers. And basically what you see is that generally, apart from some cases, generally is the trend of this increasing this radius beta index from the inner regions of the disk to the outer region. This implies larger grains inside, smaller grains outside, similar to what you predicted here. Consider that this is a logarithmic axis and this is a linear axis. And I have blanked there the regions where we either have low signal to noise or we don't have the resolution for observing. So far we are still probing a very specific region. I mean, this is really nice to be able to do this, but still we are probing a limited region in the disk, okay? And if you compare with the models, essentially, we are still probing this outer disk here, okay? Which is actually well described by this declining grain size distribution, okay? You still need to slow down somehow the transport of grains, okay? Because this model that I showed here is one of the models that did run without the radial transport of the grains. You put that in, then all the grains will move in. And so you need a way to stop the grains. One thing that has been talked for a long time was the possibility of having pressure plugs in the disk created by the gas dishomogeneities that would confine grains. And so for years, we have been modeling what to expect out of simulations of disks with these homogeneities in the gas. This is just an example of a spiral instability that in the gas that creates a density instability and then confines the large grains into the spirals. And this is what you would observe with ALMA of the spirals and you would observe of the spectral index, okay? So confining the large grains in the spiral arms and in the center, and the small grains outside and in the interspiral positions, okay? Obviously, when you observe that it's never exactly as a simulation, but still ALMA is observing confinement of grains in some special cases. These are from the cycle zero observation, so these are limited angular resolution and sensitivity, and I mean new results you should expect that will come out of cycle 2 and cycle 3 on really measuring the spectral index as a function of position in the disk. Another key thing that we are able to probe now with ALMA, as I alluded to at the beginning, is the gas component at high sensitivity and also the more complex molecules. So these examples are simple, abundant CO gas that shows that the gas is also present in the inner regions of these disks where the dust grains are depleted. If you look at more exotic molecules, you can detect also some interesting features, and this is one of the most interesting results that came out in this area out of ALMA, so the direct detection of snowlines in the disk, so the transition from the gas phase to the solid phase of some key molecules. In this particular case, this is an indirect detection, chemical detection, so it's indirect detection of the CO snowline in one of these telephone number disks, and is traced by the fact of the high enhancement of a molecule, HDCO+, which otherwise would be destroyed by CO in the gas phase. So when the CO is in the solid phase, this molecule is abundant, and this marks the transition between CO gas and CO on ice. And CO is the second most abundant molecule after, well, third most abundant, if you want, after hydrogen. It's molecular hydrogen, which obviously we don't see. and water. Okay? The water snowline is expected to be much closer in to the center of the disk. But the detection of snowlines is interesting because it might be connected also to processes of enhancing the formation of large grains and planetesimals. And so this is something that we have been looking at and that we are also discussing with Sebastian and Keys for looking at the radial side whether we can model what we see. And basically what we do observe in this particular disk is that we see an excess emission at the CO snowline, which might be interpreted as a concentration of dust grains. Actually, Sebastian is telling us that this is not grain growth, it's just the depletion of grains just on the other side of the snowline. And so this might be actually the simplest interpretation of these results, but it shows you that with ALMA we are now at the level of sophistication in the observation of disks that we have to go to the second order effects to understand our observation. So it's time to move to high Z astrophysics, I guess. So you say hello, sorry guys. Okay. So I think I wanted to close this part on ALMA, just giving you on ALMA results on this, just giving you what can we expect in the near future. So we are at a stage in which we can do surveys of disks. This is actually a postage stamp of an ALMA survey of protoplanetary disks in Lupus, in this particular case, at relatively low angles, but still 3.4 arc seconds, so not very low angle resolution. But we are in the area of population studies for the first time for protoplanetary disks. We are not taking years to assemble a sample of 20 disks. We now take a few hours to get 100 objects, so that's a major breakthrough. Another breakthrough that we are going to have soon is polarization observations, and Kataoka-san here has made a lot of predictions of how the grain growth may give a signature in the polarization of disks. So again, obviously this is a key thing for the future to basically use also these measurements to constrain the growth of solids in disks. And the other thing in the future, obviously, is looking at molecules, complex molecules, and biologically relevant molecules in disks and cores. So water may be feasible with new receivers that we are putting on ALMA in some cases. It's still tough, but it's obviously super interesting to measure the abundance of water in disks. And then go into even more exotic things like trying to detect complex molecules that might be hard even for the new receiver on ALMA, but definitely we should try and will be trying. So the near-term expansion of ALMA that you might expect, these are the goals that we had last year for a 2-year time frame. So the first was to go to the long baselines and allow the measurements like the one on HL tau. Obviously, we have demonstrated that this, we have done that, and the new observations will soon come out from the long baseline campaign that we had a few months ago. We are now working on improving the spectral scans, which is interesting both for galactic studies of the chemical complexity, of course, but also for the redshift cycles. Okay? And this still has a lot of overheads that we are slashing down, and so new things will come in that area. Obviously, we have more antennas now. I'll tell you how many antennas we have in cycle 4 in a minute. So the sensitivity is also improved. So this Wiggle Mister is ready for cycle 4. It's not yet there, but it's ready for cycle 4. We are building new receivers that were scoped in 2005 and will get to the telescope in the next few years. So that's ready because it takes still a few years. And we have re-implemented millimeter LBI and the solar observing mode that is also part of the scope and will be started at the next step in cycle 4. Okay, in the long term we have our view of the development plan. This is a very colorful picture that we did in Japan, obviously. That's why we have these colors. And basically it's telling you that this is the past. So we have earth science, we have ALMA delivered as construction, we are having limited LBI next year and solar observation. We have the band file, which will allow water in the local universe and atomic carbon at very high redshift soon, in 2017, 2018. And then in the future, we already have a longer-term plan for advanced receivers in the low frequency domains. These are not yet approved, that's why there is a question mark, but the development is in the last stage, both for band 1 and for band 2/3, which is a new band with higher sensitivity. The extremely long-term goal, projecting farther away in the future, so the vision for the long term, I think, is still under discussion, obviously, but there are a few major guidelines that we think are important. One is to basically improve to the maximum that we can the infrastructure that we have. Okay, so we have antennas, we have an interferometer. The next thing is to improve the receivers and the instantaneous coverage of the bandwidth in such a way that we improve the efficiency and the sensitivity to the maximum possible with the current infrastructure. This is something that is easy to some extent, it's just a matter of time. The thing that is less easy, more expensive, but would be interesting for science goals is the higher angular resolution even. And going to longer baseline is certainly possible in the 30 to 50 kilometer range, some optimism. But I think the key problem here would be sensitivity. So it has to be linked with this and possibly also with an increased number of antennas, although that obviously is more difficult to obtain. And but this is something that is interesting. The last part is one of the weak sides of ALMA. We always promote ALMA as the can do everything, cannot do everything. One thing that ALMA does not do efficiently is large-scale mapping. So one thing that is not good for ALMA is to study, for example, the detailed structure of nearby molecular clouds. Yet it's so important to understand star formation. Okay? So obviously in this area, there are two possible ways. One way is implement more effective mapping capabilities with the current ALMA, doing panoramic detectors for interferometry, with a question mark because nobody has ever done this, so it's not something that you can do tomorrow, and is a lot of data rate. And the other option is obviously complement the ALMA with improved single dish capabilities with a larger single dish telescope. Okay? And there are several ideas on that, and it's one thing that I think should be pushed for the long term if we want really to help in this area. And finally, the role of the archive will be even more prominent than it is today. I think the ALMA data sets, if you look at the richness of the ALMA data sets, you see that the PIs are only using a tiny fraction of the possibilities. So archive will be the big word of tomorrow. The challenge for us is to allow the use of the archive, which is not easy, because the archive contains data, contains reduced data, but it's not easy to understand what is in the archive and to get what you really want on one side. And on the second side, reprocessing is an important point. And reprocessing of ALMA data is not trivial. And so one of the things that we are looking for the long term is the paradigm both to data and results to users, in the sense that reprocessing will not be done by users at home, but rather on their archive request, and then we get the reprocessing results. But this is really for the future. Back to Earth, and this is my last slide, and then you are free to go and rest. Is what to expect for cycle 4. I'm sure you wanted to know this. And for cycle 4, we are basically, there's an announcement already in our science portal. we expect to make available 40 antennas from interferometry, the main array. This is guaranteed for the project, okay? So this means that no less than 40 antennas will be used to do science. Yes, so it will happen, but no less than 40. The baselines will go up to 13 kilometers for the low frequency bands and a little bit less for the higher frequency bands, because still there are difficulties in the high frequency calibrations at longer baselines. We will offer spectral line polarization. So far we have been offering only continuous polarization. We are moving to spectral line. Millimeter behind and solar observing modes, as I said. And another two big changes in the next cycle will be these two. The possibility of having ACA standalone observations. This is particularly relevant if you want to observe large structures with limited angular resolution. So this is an important possibility. And large programs. Large programs in the ALMA context means programs that are larger than 50 hours, but can have co-PIs from different ALMA regions, which means that in some sense you bring together groups from different regions and you don't charge all the time of the program to one region, which is what's happening at the moment with normal programs. There are also several minor details, let's not go into these details. The deadline is expected to be on April 21st, it will be 1 year cycle like this year. And finally, the band 5, which is the new frequency band, is on track to be offered for cycle 5. Okay, this is all what I wanted to say, and basically this is a summary that contains what I just said. And the key point is that we are delivering transformational science, as our motto says, on the field of starting band formation and also on other fields. Stop here.
Thank you, Leonardo. So let's open for questions, and traditionally we start with the students and postdocs. So, yes.
How has
I'll just bring the microphone, just
how has the usage changed since the cycle 0 statistics?
The usage, okay. So how is divided by science topics? Has not changed significantly. We are still dominated by protoplanetary disks, interstellar medium star formation, and galaxies in the two flavors. Galaxy evolution, which means, from population of galaxies from redshift 3 to 1, and then they got the tail galactic stars. So these are still the three main things. To be honest, I didn't show any result from the stellar and solar system cases. We have a few, and we have a few very nice results in those areas as well. So, for example, I want to mention that in the stellar case, we have several very nice studies. One of them is actually the detection of molecules and dust in supernova 97A. Those are very nice results. And also because allowed to study the chemistry of the explosion to some extent, the molecules that are forming there. And then we had studies of the Alpha Centauri system at millimeter wavelengths. There was also very nice, and late type stars and so on and so forth. And in the solar system, actually we suffered from some early birth problem, in the sense that it was difficult at the beginning to do the observation properly because we had some problems with ephemerides, and so we basically were not looking at the right direction. How embarrassing it may be, but this was what happened at the beginning. So it took a bit of time to get that properly sorted out, and then we had some problem with the data reduction software to work for solar system cases. But now we have a number of results of chemistry of comets, for example, and also on the atmosphere of Venus and Titan and other papers. So it's coming that part as well.
Any other questions by students, postdocs, or by everyone?
So with the EELT coming soon,
You are not.
yeah. Of course, there's going to be a demand for similar resolution, sensitivity, sub-millimeter observations. So I realize it's maybe a bit much to ask ESO to take care of all of that across the full wavelength range. But are there any plans to actually extend the ALMA array to, at some point, you actually said, just throwing more brute force at it will, in the end, give you more resolution, more sensitivity, and especially at the higher reaches, it's going to be very relevant. Are there any plans in that direction?
Yes, as I said, this is one of the directions we are looking at. This is still at an embryonic phase, no? In the sense, we need to build a vision of where we want to be in 2030, and then after we have the vision, we need to go around and find the money, which again is not easy. And it's not impossible, as I tried to say, so it's certainly possible to expand to 20-30 kilometers distance, meaning that there are sites nearby that you could use at the same altitude and that you could tie together. Okay? Then the problem if you do this is that you need more antennas because you cannot get and transport one antenna from here to there. And as soon as you want more antennas, it's expensive. It's expensive. But that's one option that we are looking at, and it depends on the push that we have from the community. In some sense, if the community is pushing in this direction, then this is a possible direction, definitely.
And in principle, it fits on the plateau.
No, as I said, we have used all the plateau essentially. So the plateau goes, I mean, we could spend 1 or 2 kilometers on the plateau. That's not what we are looking for. So we could go to nearby places up to 30 kilometers, which means that you have to build the road, you have to lay down the fiber. It's expensive.
I also have a non-scientific question, and the topical word is expensive. So, how much is an ALMA observation? Just to get some general price to compare it with other facilities like James Webb.
That's a very good question, which I don't know the number off the top of my head. We can review it and go back tomorrow. The total cost of the ALMA construction is $1.5 billion. Okay? And operations is 60 million, all operations, so on-site and off-site, is around 60 million per year. Then you can imagine a 30-year time span and die if you want. But that's roughly speaking about it. Yeah, you can do it if you plan.
I'm thinking again about extending capabilities for the future. So you talked quite a lot about increasing even more spatial resolution for continuum observations, but another goal could be to try to get line sensitivity on the same kind of spatial resolution that we can already do with the continuum now. So that might need much bigger dishes. I do not have a good feeling of that.
It requires some bigger dishes because obviously the main difficulty is that increasing the sensitivity in the continuum is relatively, well, it's not easy, but you can do by increasing bandwidth. No? Okay. The lines obviously are limited by the spectral resolution, so it goes at the ratio between the spectral resolution and the bandwidth. So you need very large dishes to compensate for this. Because we have bandwidths that are on the order of at the moment we have 8 gigahertz with polarization, and you want to compare with the spectral resolution that is less than a megahertz. So there is a factor of 1,000.
I have another question. So you were talking about data volume, right? So is there a possibility in the future to do sort of on-the-fly data production so that you can actually store a much smaller amount of data?
So one of the key issues, especially if you go to long distance, but also we dump data at a range that does not destroy signal, which means that it does not smear out the variation in the atmosphere. We can calculate. Okay. So, and we have these variations, something that I didn't show, but these variations are on time scales that are seconds. And at the moment we are tracking them with water vapor radiometer, so we have a system essentially that measures fluctuations on the same time scale. And offline, we do the corrections and then we do the averaging. So one thing that we are looking for is basically do this correction online. We have already the software that works online. It's just that we haven't there yet to switch it on and do it, because once you do it, you don't correct. You see, no, once you have applied the correction and you have averaged every 20 seconds, you don't go back to 1 second anymore. So
Yeah,
that's,
you could at least for the test phase store
yes.
both.
Yeah,
And then,
that's what,
and then see if the system works, and if it doesn't, you still have to back up later.
yeah, that's what we do. That's what we do. It's not trivial because it goes through basically a model of the atmosphere to some extent. So it goes through the network of weather station that we have and so on. But that's definitely cool.
Okay. Any further questions? If not, then let's thank Leonardo again.